All right, let's dive in. Today, we're talking about the one algorithm that honestly is the foundation for almost everything else in machine learning. It's simple, it's powerful, and it's called linear regression.
I mean, it sounds like something straight out of a movie, right? Teaching a machine to predict the future. But that's really what we're doing here. So the big question is, where do you even begin? How do you get a machine to make a smart guess about something it has absolutely no prior experience with?
Well, we start with something really tangible, a problem you see everywhere when you're starting out in machine learning, predicting house prices. The whole idea is, if we know a couple of things about a house, like its size, can we make a really good guess about its final price tag?
Okay, before we get any deeper, we need to get on the same page with some lingo. It's super simple, I promise. That big list of old houses we have, with their sizes and what they sold for, that's our training set. It's the textbook our model studies from. Then, each piece of input info, like the square footage, we call that a feature. And the thing we're trying to guess, the final sale price, that's our label. See? Training set, feature, label. That's it.
So, we've got our data, we know what our features and labels are. Now, how in the world do we build something, a model, to actually connect them? The simplest approach is often the best place to start.
And believe it or not, the answer here is shockingly simple. We're going to draw a single, straight line. That's it. The whole idea is to use this line to describe the relationship between how big a house is and how much it costs.
And that brings us to our official definition. Linear regression is just the name for the process of finding the very best straight line that slices through our data points. The line that gets as close as possible to all of them. That line is the model. It's what makes the predictions.
Now, any straight line is really just defined by two numbers. First is the weight. You can just think of this as the slope. In our example, it's kind of like the price per square foot that our model is learning. The other number is the bias. That's just where the line starts on the vertical axis. It's like the base price of a house before you even consider its size. If we can find the perfect weight and the perfect bias, we've got a working model.
Okay, so we know we need to find the best line, the perfect weight and bias. But how does the machine actually do that? This is where the learning in machine learning really happens.
I mean, you could draw an infinite number of different lines through those data points. So how does the algorithm sort through all of those possibilities and land on the one single line that's going to give us the most accurate predictions?
Well, it starts by figuring out how wrong it is. We use something called a loss function. All this does is measure the distance between our line's price prediction and the actual price for every single house. You add up all those little errors, and you get one number, the total loss. A huge loss means your line is way off. A tiny loss means you're getting really close.
So the mission is crystal clear, right? We have to get that loss number as low as humanly or machinely possible. And the tool we use for this is a brilliant process called gradient descent. I want you to picture the loss as this huge, sprawling valley. Our perfect line is sitting at the very bottom. So gradient descent is like placing a marble on the side of the hill. The marble looks around, finds the steepest way down, and rolls just a tiny bit. Then it stops, looks again, and rolls a little more. It just keeps doing that step by tiny step until it finally settles at the absolute lowest point. That's how we find our best line.
And this whole thing runs in a cycle we call the training loop. It's super straightforward. Step 1, the model makes a guess with its current line. Step 2, it uses the loss function to see how wrong it was. Step 3, it figures out exactly how to nudge the weights and biases to make that error a little bit smaller. And Step 4, it does it all over again, and again, and again, thousands, sometimes millions of times, getting a tiny bit smarter with every single loop.
Okay, so our training loop runs, and we find a line that fits our house price data beautifully. The loss is super low. We're done, right? Well, not so fast. This brings up maybe the single most important question in all of machine learning.
Has our model actually learned the real underlying connection between a house's size and its price? Or did it just get really, really good at connecting the dots for the specific houses we showed it? This is the critical difference between true learning and just plain old memorization.
Let's think about it with an analogy. Picture two students. You've got Extraordinary Ellie, the memorizer. She crams the answers to every old exam. She'll get a perfect score if she sees those exact questions again, but give her a brand new problem and she's totally lost. Then you have Inductive Irene, the pattern finder. She works to understand the concepts. She might only score a 90 on the old tests, but she'll also get around a 90 on a completely new exam because her knowledge actually generalizes. In machine learning, we always want to build an Irene, not an Ellie.
This problem, the Ellie problem, has a name: overfitting. It's what happens when our model gets too obsessed with the training data, learning every little quirk and bit of random noise. It looks perfect on paper, but it's useless in the real world. What we're shooting for is a good fit, a model that ignores the noise and captures the true underlying trend, a model that can make reliable predictions on houses it's never seen before.
And that's the real takeaway here. The goal is never to get a perfect score on your training data. The goal is to build a model that has learned a genuine pattern, one that generalizes well and can be trusted to make useful predictions out in the wild.
So now that we've got the theory down, how does this actually happen in practice? Does every single data scientist have to, build all of this from the ground up every time?
I mean, if you were going to do it all from scratch, you'd have your work cut out for you. You'd have to code the model parameters, write the loss function yourself, implement that whole gradient descent process, and then manage the entire training loop. It's a lot.
But, and this is a huge but, you almost never have to do that anymore. Thankfully, modern tools called deep learning frameworks like PyTorch and TensorFlow do basically all of that heavy lifting for you.
These amazing libraries are like toolkits with all the parts you need right off the shelf. They've got the standard loss functions ready to go, a whole menu of optimizers just like gradient descent, and they handle the entire training loop for you. It lets you focus on the big picture, designing your model instead of getting bogged down in the nitty-gritty.
And that really brings us full circle. This simple little line with just two numbers defining it is the great-great-great-grandfather of the huge complex AI models we hear about every day. And think about this. We just saw how even this basic model struggles with that core problem. Is it actually learning, or is it just memorizing? That exact same challenge, that same fundamental tension, exists in those giant models too, just on an unimaginable scale. So the next time you interact with some cutting-edge AI, just remember the ghost of this simple line inside of it and ask yourself, has it really learned, or has it just gotten incredibly good at memorizing? Something to chew on. Thanks for digging into this with me.